Hello, I hope you're doing well. This question number 5 from May 25 Time Zone 2, paper 2, is about the Compton scattering experiment. And in this question, you have to justify, you have to explain that is the Compton scattering experiment why it gives a better evidence for the particle nature of light than the photoelectric effect. So you have to compare with photoelectric effect. So now you know already that the photoelectric effect gives the evidence of particle nature of light, but the Compton effect proves something even deeper. Okay, and what is that? Let us go for understanding of photoelectric effect in a brief manner, right? So what happens in a photoelectric effect? These are the photons of light. Okay, so these photons of light are consisting of a very specific category of electromagnetic wave. And since you should understand that which lights actually can exhibit the photoelectric effect only. So those are from infrared to X-rays, sorry, ultraviolet. So any light between them, obviously from infrared to visible light. And in the visible light, we have the seven lights whip wire, right? So the point is that why only these lights exhibit the photoelectric effect? Because in the photoelectric effect, the photon, when it hits the metal surface, it gives out all of its energy to the electron, which is near the surface. Okay, so when electron grabs that energy, it instantly comes out of the metal, right? It immediately comes out of the metal by getting that energy from the photon. So that's why, so energy of photon is completely transferred to whom? Completely transferred to the electron. So that's why it gives the evidence of law of conservation of energy, right? So we don't see exactly that how the momentum is conserved, which we exactly see in the Compton's effect. And then that the electron acquires that energy, and if that energy is enough, means it is equals to the work function, or it is more than the energy required, then this electron is ejected from the metal surface, and with the rest of the energy it moves, right? So, but in a Compton scattering effect, in the phenomena, what happens? A high energy, a very energetic photon of X-rays, because I already told you that these are the lights which exhibit the phenomena of photoelectric effect, because they give the energy. But X-ray is the light which whose photon is so energetic, and because of its extremely small wavelength, that it doesn't give 100% of its energy, it just give a fraction of its energy to the electron which is at rest. So what happens then? This photon with the rest of the energy, which is obviously less, it scatters. Okay, whereas this electron recoils in this direction. All right, so that's why we observe not only the law of conservation of energy in the Compton effect, but also the law of conservation of momentum. That's why the Compton scattering experiment have the upper hand over the photoelectric effect. So let me show you this. And momentum are both delivered. So students, let's quickly see the Compton scattering provides evidence for the energy and momentum, right? Whereas the photoelectric effect provides evidence for the energy. This is what Mark's scheme says. Okay. Now our next question, in which they show us that an X-ray photon is rushed towards an electron which is at rest. Okay. And we are given the wavelength of this photon, and you can see that this wavelength is smaller than the wavelength of ultraviolet light. So that's why I'm considering it in the region of X-ray electromagnetic spectrum. Okay, so you can see that it is by the way, we can say 6400 femtometer, right? Means stands for negative 15. Okay, so which is obviously in the X-ray spectrum. Okay, and its energy is given 0.194 mega electron volt, and it is incident on electron which is at rest. So after the collision, that is obviously an elastic collision. Okay, So the photon is scattered. The photon scattered because it have now the less energy, so it's scattered in this direction. All right. And whereas the electron recoils. Okay. So the first question is, dear students, outline why the wavelength of scattered photon is longer than that of incident photon. Okay. Now, to answer this question, which is very easy, okay, you need to understand and you have to revise again what the Planck's assumption says to us, right? What is the Planck's assumption? Right? The light have a energy which is delivered, and that energy depends on the frequency, right? This energy exists in the form of packets of energy, right? And this is called a photon. Every photon have a certain frequency because it travels in a form of wave, but when it hits to some place, it collides just like a particle. This is the wave particle duality. So E is equals to hf, right? Okay. And moreover, if we open this equation, so you can also write C is equals to f lambda, right? This is the equation of the wave. Okay. So f is equals to c over lambda. So if we put the value here, so it is hc over lambda. So what conclusion that we draw from here, that the energy of every photon of the whole electromagnetic spectrum is inversely proportional to wavelength. So the longer wavelength carrying light have will have a less energy, and a shorter wavelength carrying light will have a more energy, just like we see the X-ray have. Okay. Now, so this is the reason that, okay. And secondly, dear students, you know that the photon of X-ray has delivered energy to electron due to collision. So here let me show you that this is a, imagine this is a wave, okay, and this is the wavelength of this photon, right? This is lambda I, wavelength of incident photon. So its energy, what, how can you write it? That its energy is equals to hc over lambda I, right? And what about at this point, we see that this is a wavelength of the scattered photon, right? So lambda s. Okay. So since you know that the energy is delivered, so energy of the scattered photon is obviously less than the energy of the incident photon. That's why the wavelength of scattered photon will be more than the wavelength of incident photon, because energy is inversely proportional to wavelength, right? So students, you see that the photon loses energy, and it transfers to the electron, and energy is inversely proportional to the wavelength. That is what Mark's scheme says. Now the next question, show that the energy of scattered photon is about 0.17 MeV. By the way, we know already that what is the energy of the incident photon, and that is 0.194 MeV. And you see it is more than the energy that we need to prove, 0.17 MeV. Okay. So how can we prove it? We know the law of conservation of energy is not even violated at this microscopic level. All right. At this subatomic level. So what happened? How can you find that energy? So the energy of the incident photon is equals to hc over lambda I, which you know 0.194 MeV. This is the total energy of the system, you can say. When they collided just like the two billiard balls. They collide with one another, right? Because the momentum is transferred, energy is transferred. Okay. So it's a perfectly elastic collision. Okay. Now what will happen? I told you that the photon has scattered, right? So we can draw like a long wave like this. All right. This is a photon, and at what angle the photon is scattered, that angle is theta, whereas this is an electron that moves in this direction. All right. So we need to find out the energy of this scattered photon, and we already know that what is its wavelength. So you can use the same equation, dear students. And which one is that? So E s is equals to hc over lambda s, right? So let us put all the values. 6.634 times 10 to the power negative 34 times speed of light over the wavelength of this, which is, we see that it is 7.47 times 10 to the power negative 12. So I'm going to put here 7.47 times 10 to the power negative 12. Okay, so our answer will be in the unit joules. Okay, so if you want to convert it into electron volt, you can divide your answer with 1.6 times 10 to the power negative 19. Okay, so I have calculated and we got 2.66 times 10 to the power negative 14 joule, right? So we need to convert it into the electron volt. So 1.6 times 10 to the power negative 19, and now its unit will be EV. Okay, so let us see what answer do we get. So it is 166,250 electron volt, right? So if you convert it into the mega, means you can also write it 0.166, right? Or if you round off, right, 0.17 times 10 to the power 6 ev, which is 0.17 mega electron volt, right? So this is the energy of the scattered photon, right? So the next question is, calculate the kinetic energy of recoiling electron. Right now, we can obviously apply the law of conservation of energy, right? Of energy, because according to this law, the total energy of the photon is delivered to the energy, I mean, the energy of the scattered photon plus the kinetic energy of this recoiling electron. So it is 0.194 mega electron volt is equals to 0.166 mega electron volt plus the kinetic energy. So if you subtract it from both sides, so that will be the kinetic energy of that one. So students, answer is 0.028 mega electron volt. By the way, just for your information, that this is a kinetic energy, but according to the de Broglie hypothesis, that which applies on the matter waves, this electron will also have an associated wavelength, okay, which you can find out by this equation, right? So okay, now let's move to the next question. For an electron, we are given this value. Okay, now this, you know what is this? This is called this is called the Compton wavelength. Okay, Compton wavelength. Okay, so according to this Compton scattering experiment, if, because you know that the wavelength of scattered photon is more than the wavelength of incident photon, right? So if we take their difference, and their difference is called the Compton scattering, okay, Compton shift basically. Okay, and its equation, which is mentioned in your data booklet, is h over m0c into 1 minus cos theta, right? Now its derivation is not included, right? So but this equation, you should know that how can we utilize it. Okay, so what we need to find out, we need to find out theta. So delta lambda, as I already told you, is lambda s minus lambda I, is equals to the Compton wavelength, h over m0c. M0 is the rest mass of electron, and h is a Planck's constant, and 1 minus cos theta, right? So dear students, this is called Compton shift, right? Compton shift, and its value is given 2.42 times 10 to the power negative 12 meter, right? So why not if we take this term on the other side, or you can divide on both sides. So basically your formula is this now, over h over m0c is equals to 1 minus cos theta. Okay, now let's put all the values. The wavelength of scattered photon, if you remember, it was given 7.47 something. So it is 6.40. This is the wavelength of incident photon, time 10 to the power negative 12, divided by the Compton shift, which is 2.43. It is mentioned in the question, time 10 to the power negative 12 is equals to 1 minus cos theta. So I calculate all and I tell you then what is our answer. So its answer is 0.44, right? And you can also write it like 1 minus 0.44 is equals to cos theta, right? And in the next step, so cos theta is equals to 0.57, I think 56. So now theta is equals to inverse of cos 0.56. And finally, dear students, the angle is the angle of the scattered photon is. So it is 55.9 degrees, okay, which you can round off 56 degrees. So this is an angle of scattering of photon after the collision, right? So yes, you see that this is our answer, 56 degrees from the mark scheme. Okay. So I hope you understand this whole solution, and let me know in the comments and subscribe this channel and share this video with anyone.